Hey, chemistry. It's let's see, Tuesday, April 21st. Can you guys stay in there with me? Just just kind of like keep looking at these videos because this is important stuff. It's going to make it a whole lot more tolerable for you when you're in college if you listen to my videos and you follow along with me in the book. I, I just got the word that we're going to be doing some ACT prep next week. I'm going to be weaving it in with some more of what we're doing here. And trust me, I want to do both. It's both is going to help you, the ACT prep and the further into this textbook. Right now we're on page 473. I would like to finish chapter 14 and chapter 15. I really need for you to know what acid-base titration is all about. But before we do that, you need to understand the theory of acids and bases. And so that's why we're doing chapter 14. I gave you a quick breeze through chapter 13 yesterday. And so here we go. In the middle of chapter, page 473, you can see that nitric acid, HNO3, when you put it in water, now yesterday I went like this, but we're not going to do that today. We're going to make water one of the reactants. And so what do you get when you put that in there? Well, this breaks off. And the reason that breaks off is because water has a positive end and a negative end. It's polar. You can't see that. I'm going to go green. And so these polar water molecules are polaring apart this molecule of nitric acid. And it pulls the hydrogen off. But as soon as it starts swimming around in a solution of polar water molecules, it's accepted by the polar water molecule, and it makes it not H2O, but H3O, and it brings its lack of an electron with it. In the meantime, that electron goes over to the nitrate. Now, these are aqueous. They're swimming around in solution, water solution. It's a liquid. And that you can call it aqueous also. It starts out that way. They call it a liquid in here, but I like aqueous. And so this thing has a name. And in chapter 13, which we didn't get to cover very well, it's called hydronium. So what Arrhenius said was that an acid is a chemical compound that increases concentration of hydrogen ions. You could say an acid is a chemical compound that increases the concentration of hydronium ions. Hydrogen ions become hydronium ions because they attach to the water. Okay, and what's another acid? The classic acid is hydrochloric acid. Aqueous, we're going to have water, and it's going to form hydronium ions and chloride ions. Those are aqueous also. And you got to know how to be doing those ionic equations. That's chapter 13. Unfortunately, we didn't get to do that in detail. Turn to page 474. You'll notice that the strong acids are on the left in table 3, and the weak acids are on the right. You notice those equations have a little bit of dissimilarity. The ones on the left have one-way arrows, and the ones on the right have two-way arrows. That's the reason that they're strong acids or weak acids. You see, weak acids reverse on themselves. Let's take the second weak acid listed. Do you know what the name of it is? H3PO4. That's called phosphoric acid because phosphate is PO4 and 8-ic means we call it phosphoric acid. And it takes 3 hydrogens to balance out the -3 phosphate ion. And so you add water to that, it forms hydronium ions, and then the hydrogen phosphate ion, -1. Do you see that? Well, it reverses on itself and it goes back to its molecular form, H3PO4 and water. It does that after it's ionized very slightly. And that's what makes it a weak acid. It is going to the right and forming a few ions, but after it forms a few ions, it drives back to the left, and the molecular side, the left side, is more quantity. Whereas the strong acids, they 100% ionize. Say that. Strong acids 100% ionize. Strong bases 100% ionize. If they 100% ionize, they only get a one-way arrow, and all of that stuff on the left-hand side of the reaction becomes product, ions, on the right side of the reaction. And so that's why there's a one-way arrow. It's a strong acid. But let's just read the definition. Strong acid is one that ionizes completely in aqueous solutions, water solutions. And a weak acid is one that does not. It releases only a few hydrogen ions, and then it turns around and heads back where it came from. So that's a strong acid, HNO3, nitric acid. And this is a strong acid, hydrochloric acid, one arrow. So what's a weak acid? On the bottom of 474, the classic weak acid is Chaku. And that's the way I'd like for you to remember. CH3COOH. All acids have hydrogen on the front of them, except for vinegar or acetic acid. This acetic acid has hydrogen on the end because the hydrogen is appended to the oxygen. The hydrogen is not attached to the carbon in reality. So they stick that over there in that equation. Okay. We add water to this thing. And so what kind of ions are you going to get? Hydronium ions, aqueous. And what else are you going to get? You're going to get this acetate ion, aqueous. Now this gets a two-way arrow because it's a weak acid. So as soon as you form a few of these hydronium ions and acetate ions, opposites attract, and they go ahead and slam back together again and reform these molecules over here. In fact, only about 3% of the solution ionizes. So it's not a really good electrolyte. What are electrolytes? Acids, bases, and salts in solution with water. And these are just acids and bases in chapter 14. We're not dealing with electrolytes that are salts in chapter 14. Okay, so that's the classic weak acid. Which way does it drive? Just to the right, or does it drive both ways? It drives both ways, and it sets into what we call equilibrium, two-way arrow. It's an organic acid because it comes from a living thing. Okay, on the next page, 475, bases. Take a look at table 4 and tell me what bases have in common. Strong bases all end in hydroxide. Calcium hydroxide, strontium hydroxide, barium hydroxide, and all these hydroxides. So Arrhenius said, a base is something that produces hydroxide ions. So let's take the classic strong base, sodium hydroxide, and let's put it into water. Now this is a metal, non-metal. So when we dissociate it, break it apart, we're going to go ahead and put H2O up there, not as a reactant. So the bases are predominantly metal, non-metal, but there's this one here that's the classic weak base. In that case, you're going to make water a reactant. Okay? And so here's what's going to happen. Up here, you're going to get your sodium ion. It's +1, floating around. This is a solid. And you're going to get your hydroxide ion. And it's floating around. Aqueous solution. Now this down here works differently. The hydrogen breaks off and you're still getting, no, you're not getting hydronium ions, excuse me. In this case, the water is going to donate a hydrogen. This ammonia molecule is going to pull that hydrogen right out of the water, and it's going to be NH4. And it's going to be positive. And what's left behind with water when you pull one of the hydrogens off? Isn't it just OH? These are aqueous. And so in this case, the water is a molecule. All right, it has a negative end and a positive end. And this is a positive and that's a negative. And so the negative end of the water molecule pulls that off and it floats around. And the positive end pulls this off and it floats around. In this case down here, you pull the water molecule apart, that ammonia, because it's polar also. And it polars it apart. Okay. Now, what is it that makes it a base? Is it the sodium ion? No, it's the negative hydroxide ion that makes that solution basic. What is it that makes this a base? Is it the positive? Oh, by the way, this has a name. Is it the positive ammonium ion that makes it a base? No, it's the negative hydroxide ion that makes it basic. That's what Arrhenius said. This is just floating around in here just enjoying the show. That's what makes it basic. This is just floating around just watching the show. That's what makes it basic. Okay, now what about strength of bases? Well, this is a strong base. And this is a weak base. So since this is a weak base, it gets a two-way arrow. It does not 100% ionize. It breaks into these ions. And then as soon as it breaks into those ions, I don't know, let's say 3%, 5% of them are of the whole solution is ions, and they reform and they re-go back to molecules. And so it makes it a weak base. This is strong because hydroxide is right there packed into the formula unit, and you break those things out. You get 100% ionized here. You do not get 100% ionized there. And so you can see on 475 that on the weak bases, you got ammonia, and then you've got this other thing. It's some, I don't know what it is. It could be caffeine, I'm not sure. It's got nitrogen in it. You know how they say take the bitter pill? Aren't bases bitter? So that's probably some medicine of some kind. And so it contains nitrogen, and you can tell that that would be the bitter pill. Now, on page 478, we're going to go into acid-base theories, and I'm going to do that on the next lesson.